Okay, welcome to Chemistry Module 16, Part 1 with Mr. C. As usual, if you have any questions, go ahead and contact me at mrc@mrcscience.com. Many of you may be very happy to see we're on the last module of the book, so we're getting there. Okay, so we're going to talk about something called reduction-oxidation reactions, often referred to as redox reactions. So I like how your book puts it in the early beginning. How you ever wonder how a battery works? Well, a battery works via redox reactions. It relies on something called an oxidation number. I think the way I'm holding my pen might be causing the problem. Let's see. There we go. Oh, that's worse writing than I've ever had. Okay, oxidation numbers or oxidation reactions. So let's talk about the two types of reactions. This kind of combines them. We know there are ionic reactions, or ionic molecules, and there are covalent. Why won't my pen behave itself? There we go. Ionic and covalent molecules. We remember that ionics, one atom steals the electrons from another atom, thus forming ions, positive and negative. Covalents, they share electrons, thus the electrons spend some time around both atoms that are bonded together. We also learned that that sharing isn't always even. Sometimes something with a more electromagnetic or electronegative atom will hang on to the electrons more than the other ones. So that caused us to learn about polar covalence. Like our friend carbon tetrachloride, CH4. Remember that it's got the 4 H's around it on one carbon, but carbon is a much more massive molecule than hydrogen, and so it tends to hang on to those electrons more firmly, and thus we got a polar covalent with a slight positive charge on the outside. So polar covalence. So we're going to work with something called an oxidation number then. In your book, it says an oxidation number is the charge that an atom in a molecule would develop if the most electronegative atoms in the molecule took shared electrons from the less electronegative molecules. That's a mouthful. Basically, what we're going to say is we're going to treat covalent molecules as if they were ionic. So that carbon, we put the carbon in the center, hydrogen's on the outside, and instead of polar covalent bonds, now we'd say, well, carbon's going to steal the electron off each hydrogen, so it's going to have a -4 charge. Each hydrogen, because it's inside of there, will have a positive charge. So the oxidation number for carbon will be -4. The oxidation number for hydrogen will be +1. So like that. So we're going to treat everything as if it were ionic. This isn't really how it works, but this is a great way to look at some things. It helps us determine how electrons travel during chemical reactions. So it gives us an idea and helps. It's a major key in understanding some of these reactions. Okay, so oxidation numbers. Page 561, as usual, you should have your books along with. It says the sum of all oxidation numbers in a molecule must equal the charge of that molecule. So our original carbon tetrachloride had no charge, so it was neutral. So we got this carbon has oxidation number of -4. Hydrogen has an oxidation number of 1 plus 1, but there are 4 of them, so times 4, it gives us a +4. The net charge, -4 plus +4 equals 0, they cancel out. So the oxidation number has to equal the original charge. A place where this would be a little different, let's take ammonium, NH4+. So we know that nitrogen, if you look at it, has how many valence electrons free? It needs 3, so it'll take those extra 3. So ammonia's oxidation number will be +3. Hydrogen's oxidation number, just like before, it loses its electron, is +1, but now there are 4 of them. Oh, that's not +3, that's -3, sorry. My bad. So that gives us +4. So -3 plus 4 gives us an overall charge of +1, which matches our +1 here. So, pretty straightforward. Okay. Let's go ahead and walk through the examples on page 561, example 16.1, just to give us an idea. So, what is the oxidation number of iron? Iron is Fe. What's its charge? It's neutral. It has no charge. So, because there's nothing else to react with, it has all the electrons it has, its oxidation number is 0. Okay. What is the oxidation number of iron +2? So iron 2. So now, again, it's just that simple. It's just whatever it is. So its oxidation number is +2. Okay. Suppose you know that the oxidation number of magnesium and magnesium bromide. So let's write out our MgBr. MgBr2. Okay, so we know that the oxidation number in magnesium bromide is +2. So magnesium has an oxidation number of +2. There we go. What is the oxidation number of bromine? Well, it has to equal out, so to match that +2, this has to be -2, but there's 2 of them. So that means each bromine has to have an oxidation of -1, because -1 times the 2 bromines equals -2. Add the -2 to our +2, and we get the charge of the atom, which is 0. Okay. Suppose we know that the oxidation number of H is +1 and O is -2 in a compound HBrO3. So let's look at HBrO3. This might be, BrO3. So we know that this is a +1 hydrogen, oxygen is a -2. So let's take a look. We got 1 hydrogen. So that gives a total of +1. Oops. Okay, we've got 3 oxygens. We know each one is -2, so that gives us a total of -6. We want to equal 0. So, if we take our -6 plus our 1, we end up with -5. We need a +5 to zero that out. So that means that bromine, in this case, has to have an oxidation number of +5. Hopefully this is relatively simple for you. We'll see. So let's get a little more complex. This makes it a little more complex than it has to be, I think, with redox reactions. If you turn to page 562, you'll notice 562 and 563, there are 7 rules for redox reactions. You can go through these rules. Some of them are kind of important. Substances only have one type of atom. The oxidation number is the charge of the molecule, like we did with the iron and the iron +2. So if there's just one atom, it's whatever the charge is. Group 1 oxidation numbers are +1 in substances that contain more than one atom. Well, that's just like ionics. Group 1 or column 1 is +1. Guess what? Column 2 is +2, just like ionics. Number 4 is kind of weird. Fluorine always has a -1 oxidation number in molecules that contain more than one type of atom. So they're saying F always equals -1. But if you notice, fluorine lives in the second to last row, just one in front of the noble gases. So it normally, if it were ionic, would have a -1 charge anyway. Okay, number 5, when grouped with just one other atom that happens to be a metal, hydrogen's oxidation number is -1. So this is where it gets a little weird. So hydrogen almost always is +1. But if it's grouped with a metal, say we had strange thing, hydrogen silver, or hydrogenated silver. Then it's -1, and based on how many hydrogens, it means silver would have to have a +1 oxidation number here. So whenever hydrogen all by itself is grouped with a metal, its oxidation number has to be -1. That's something that's different from the ionics. I don't know that you'll ever have to remember this on the test, but I can't say for sure. Okay, oxygen has an oxidation of -2 in molecules that contain more than one atom. Well, big surprise, oxygen is in the 6th column, which, if you look at ionics, all are -2. So again, you can treat it like ionic. Number 7, if all else fails, treat it like it's ionic. So that's the best thing to do for most of those, is treat it like it were ionic, and remember this hydrogen exception here. That if hydrogen combines with a metal, it's got a -1 charge. It actually gains an electron one of the few times that happens. Okay, so let's talk about, so that's the oxidation number. And most of you will go, oxidation hashtag. Well, in my day, that was a number or a pound sign. So, okay, oxidation number. So, on page 565, you'll see there are 2 types of states. An atom can either be oxidized or reduced. So oxidation is a process by which an atom loses an electron. Reduced is a process by which an atom gains an electron. So if it's oxidized, lose only has one O in it. That's why I do not grade on spelling. Lose electron. And reduced, gain electron. Somehow my L became part of my L, or E. Okay, reduced is gain electron, oxidized, lose a reaction. They give you a little memory mnemonic of Leo says grr. You can use this if you want. Lose electron oxidation, gain electron reduction. My best way of remembering this is if something is oxidized, what does that sound like? Oxidized sounds like oxygen, right? Well, oxygen in ionic cases takes electrons. So oxygen wants to get extra electrons, thus it gets its -2 charge. So if something's oxidized, it's attached to oxygen. That oxygen has stolen its electrons, so it lost electrons to give to oxygen. Then reduced is just the opposite. So we'll go from that. So if it gains electrons, it's reduced. If it loses electrons, it is oxidized. Okay, so let's recognize oxidation reduction reactions, or what's a reduction oxidation, which is called a redox. Reduction oxidation reactions are redox reactions. Okay. So what makes a redox reaction? A redox reaction occurs only when an oxidation numbers change. So when an atom's oxidation number changes, say we had our hydrogen, it originally was plus on one side, and on the other side it's a minus. Its oxidation number has changed from +1 to -1, so it has gone through a redox reaction. Something about a redox reaction, whenever something's reduced, something will always be oxidized, and the entire reaction will be balanced. There will not be a negative, and there will not be a net gain or loss of charge. So both sides of the reactions will have the same charge. They give us a couple examples here. So let's take the first one. We got Mg plus 2 hydrochloric acids gives us hydrogen gas plus magnesium chloride. Okay, let's look at the oxidation numbers here. So magnesium's all by itself has a net charge of 0, so its oxidation number is currently 0. Hydrogen. Hydrogen, this is not a metal, so hydrogen is a plus. It always +1. It always goes to +1. Because of that, we see that chlorine is a -1 because it's with the hydrogen or because it's in the 7th column of the periodic table. Then we get to this side. Hydrogen is all by itself. When it's the only atom, even though there's 2 of them, it takes the oxidation number of the charge of the molecule, which is 0, so hydrogen now is +0. Magnesium is with 2 chlorines. We know chlorine is -1. 2 ways of looking at magnesium, so it's got a -2 charge here, so magnesium has to be a +2. Either because of the chlorine, or if you look, magnesium is probably, I don't know if it's in the 2nd row of the periodic table of elements. I should have a periodic table with me when I do this. Okay, so let's look and see what happened. Magnesium went from a +0 to a +2. So how did it get there? It had to lose electrons, right? So it was oxidized. Okay, hydrogen went from a +1 to a +0. So in order to do that, it had to gain electrons, so it was reduced. In the overall charge change and reduction, 1 magnesium went to +2, 2 hydrogens went lost to -1 or -1 lower. That equals out. So. Okay, there's another one here. Here, we'll do one more just for the fun of it. Here, you can look at sodium hydroxide and hydrochloric acid down below. It gives you an idea, but let's go look at it on your own. That way you don't have it sitting right in front of you. So, okay, for each of the following, page 568 on your own questions, for each of the following, determine whether or not it was a redox reaction. If it is a redox reaction, identify the atoms whose oxidation numbers changed and tell whether they were oxidized or reduced. Okay, cool. So let's go ahead and do these. So, oops, I got to do it over here. So let's take the first one. Cu plus 2. I don't care about states at this point. They do not come into play with oxidation reduction reactions. Plus zinc gives us zinc plus 2 and plus copper. Okay, so the oxidation number of copper here is, since it's all by its lonesome, is just its charge, so it's a +2. The oxidation number of zinc here is all by its lonesome, so it's the charge of the atom, or +0. Zinc now has gone to +2, copper all by itself has gone to +0. Is this an oxidation reduction reaction? Oxidation numbers have changed. Copper went from +2 to 0, and zinc went from 0 to +2, so yes, this is an oxidation reaction. Okay, oxidized. In order to be oxidized, it has to lose electrons. Which one of these lost electrons? To go from 0 to +2, you have to lose 2 electrons, so you gain that +2 charge. So zinc was oxidized. And then reduced, you have to gain electrons. Copper went from +2 to 0, so it gained 2 negatively charged electrons to cancel out that +2, so copper was reduced. Okay, let's look at the next one. 2H2O is decomposed to 2 hydrogen gas plus oxygen gas. Okay, let's look at this one. So we know oxygen has a -2 oxidation number because treating it like an ion, it's in the 8, 7, has to be the 6th column, and so it wants to gain 2 electrons. Vice versa, hydrogen gives away its electrons, so it's got a +1 charge. There are 2 of them, so it balances out. Hydrogen gas all by itself, what's its oxidation number? The charge of the molecule, which is 0. Oxygen's all by itself, what's its oxidation number? Charge of the molecule, all by itself, 0. Have oxidation numbers changed? Hydrogen went from a +1 to a 0. Oxygen went to a -2 to a 0. Yes, it did, so yes, this is an oxidation reduction reaction. Oxidized. Oxidized means that it lost electrons. Now it's kind of funny, but you'll rarely see that oxygen is actually oxidized. It can happen, but it's rare. So hydrogen went from a +1 to a 0. So it had to gain an electron to do that. Oxygen went from a -2 to a 0, so it had to lose electrons. So this is one of those strange times when oxygen is actually oxidized. Reduced. So you'd say, oh, it's just the opposite, but just to confirm in case you have more. So hydrogen went from a +1 to a 0. It had to gain electrons to do that, so it was reduced. Okay, let's look at the next one. Sodium chloride plus silver fluoride. Gives you silver chloride plus sodium fluoride. Okay, so let's look at this. Well, looking at the table, periodic table, or vice versa, looking at chlorine, we know that chlorine is a -1, sodium is a +2, +1. So they have to balance out. Silver, we don't know, but we know fluorine's always -1, or just by going its ions. So silver, in order to be balanced, because there's no charge here, has to be a +1. Okay. Chlorine, again, -1, because there's no charge here. Silver has to balance out, +1. Fluorine, -1. Sodium, +1. So sodium went from +1 to +1, no change. Chlorine went from -1 to -1, no change. Silver went from +1 to +1, no change. Fluorine went from -1 to -1, no change. There was no change in oxidation numbers, so no, this is not a redox reaction. Okay, let's do the last one here. Here we go, calcium plus 2 nitric acids gives us calcium nitrate plus hydrogen gas. Okay, you should be able to do this, but calcium all by itself, so what's the charge on the atom? 0, so it's got a oxidation number of 0. This is a little more complex. Let's start with hydrogen. We know hydrogen is a +1 because there's not a metal here to make it a -1. Oxygen, if you look at ionic, is -2. So that means nitrogen has to be what? Well, we've got 3 oxygens, which is -6. We want 1 hydrogen, which is a +1. In order to balance out, nitrogen has to be +5. So that 5 plus 1 is 6, balances out the -6. Okay. Calcium, let's, you can look up calcium. I believe it's a +2. I don't have it in front of me, but let's look at our nitrates here. Yeah, calcium is a +2. Okay, oxygen's a -2. Nitrogen, we don't know yet, so we've got 1 calcium, so +2. Now we got 6 plus 2 is 12, -2 oxygens. So that gives us -24. So in order to balance this out, we need 12, or half of that, because there will be 2 nitrogens. So we need a +12 here, which means 2 nitrogen will be a +6. Okay. Hydrogen's all by itself, so it's the charge on the molecule, or +0. Okay, so calcium went from 0 to +2. Hey, there's a change. Hydrogen went from 1 to 0. There's a change. Nitrogen went from 5 to 6. There's a change. Oxygen stayed the same. Okay, so there was change, so yes, it is a redox reaction. Oxidized. What oxidized means it lost electrons. Calcium went from 0 to +2. It had to lose electrons to do that. Okay, reduced. Let's look at our next one. Okay. Hydrogen went from a +1 to a 0. It had to gain electrons to do that, so hydrogen was reduced. Nitrogen went from a +5 to a +6. It actually had to lose electrons to do that, so nitrogen is oxidized. Oxygen stayed the same, nothing happened. So this is a redox. Calcium and nitrogen were oxidized, hydrogen was reduced. Okay, we'll take off from here next week in our next video. Again, if you have any questions, contact me at Mr. C at MrCScience.com. Right there. Thank you.